Well, thank you very much, Ed, for a wonderful lecture. I'll say one or two words at the end, but once we've had an opportunity to give you an opportunity to ask Ed some questions. So who would like to kick us off with a question? We have one over here. We've got a couple of runners with microphones, so please just wait until the microphones got to you.
Hello, thank you very much. I've heard about quantum entanglement, and I almost think I know about it. The puzzle in my mind is, could this phenomenon form a basis of faster-than-light communication? If you've got a thing here which is affected by what you do to something over there, can you use this to communicate?
Yeah, it gives the impression, doesn't it, that you can. So just to, in case not everybody knows about this, you can arrange to have two particles, let them be photons. You can have two photons, and they're either polarized up and up like this, or they're polarized down and down like this. And you have two detectors far apart. And the photons don't know, any more than we know, whether they're up or down until there's a measurement. It's just like when I showed the photon landing on the screen. Nobody knows where it's going to land until it lands. So there's a detector over here, and the detector over here says, this one was polarized up. We immediately know that this one must therefore be polarized up. And if we later check whether that was true, it was true. But if exactly the same experiment says it was polarized down, then that implies immediately that this one was down, and when we check, it was down. So the question is, does that mean that some information has been communicated from this particle to this particle, and because it was instantaneous, was it communicated faster than light? And my answer is no, I don't think it was communicated faster than light. I think it's just that that's the way quantum mechanics works. If you try and dream up a scheme for actually sending information from Alice to Bob using this faster than light, we don't know any scheme to do that.
Okay, who else have we got? It's got a burning question here. Yes, right in the middle on your right. Just wait for the microphone to get to you. Keep your hand up, well up in the air. Yes, that's super. Thank you.
Hi, I had a friend in Vancouver who worked for a company called D-Wave, and she told me many years ago they had a working quantum computer. Was that a lie?
Yes.
A number of labs have devices that have the ability to compute using quantum behavior, but what no device has, to my knowledge, is the ability to compute anything that cannot be computed more quickly than with a classical computer at the moment. So the promise is there for a device that can solve problems that are too difficult for classical computers. But in reality, right now, the state of the development is such that no computer exists, no quantum computer exists that can solve anything better than a classical computer. And there are technical reasons why this is hard. So D-Wave has a machine that uses quantum mechanics to help them do some kind of computation, but it doesn't deliver the dream of solving problems that are too hard to solve with your laptop.
Okay, we have one just behind you there. There we are. Great. Remember, there are no stupid questions. There are only stupid answers. So you can't be stupid. He can be stupid.
I'll try not to.
Please go ahead.
So I was wondering, with the detector at LIGO, how do they know for how long the wave was traveling before it reached Earth?
Can you just say again? I didn't quite catch what you said.
With the detector at LIGO,
yes.
How did they know for how long the wave was traveling before it reached Earth?
So, how long did it? How did they know how long it was traveling since the big explosion of black holes, or how did they know how long it took to get from the one detector to the other? The first one. Mm-hmm. Very clever people looked at this little wiggle and inferred the movie that I showed you. So from the movie, they were able to work out so from the frequency of the oscillations and from the magnitude of the oscillations, they're able to work out how big the black holes must have been and work out how they spiraled in and coalesced, and then from the strength of the signal, how far away that must have been in order for the signal to be so weak by the time it arrived here. It's all done by modeling on the basis of these little wriggles. Does that answer your question okay?
We have a hand up, sort of, I guess, 2/3 of the way back on my right, your left.
Hi. I was just wondering how metamaterials work that like bend light around themselves.
I can't see where you are.
Oh, you think she's a plant? Very good.
The problem I have two problems. One, the world's expert on this topic is sitting right here. The other is I can't see a way to answer you satisfactorily in a short amount of time. I will be happy to talk to you immediately afterwards if you like, but I think in this forum it doesn't make sense for me to try and answer that particular question. I'm sorry.
Okay, that's fine.
Anyway, we've got one right down here on the front. I'm still going to ask you to wait. Sorry, I know you're close to him, but everyone else wants to hear your interesting question, so let me just hang on a second. Here we are. Over here.
Hello? Ed,
Hello.
When you set out to build an interferometer, what are the biggest challenges you face, say, for example, with a clock or your gravitational measurement device?
That's a many-faceted answer to that. I mean, the first problem is it costs money, and at the moment you need quite a high level of scientific expertise. So you have to get a team of people who know what they're doing, and you have to get money. A key thing is laser technology. So all of these things that I've spoken about could not have happened without the progress, amazing progress of laser technology. So you have to have laser systems that are able to prepare light sufficiently, exquisitely well for the instrument to work. That costs money, but also it's just a question, is it even technically possible? So, for example, the navigating interferometer requires lasers which are at the forefront of what laser technology can do, and we work very closely with a laser company that specializes in making scientific types of laser. Then you think very hard and try and work out what's going to go wrong, and then build it. And at some point, which is more or less now, the device is sufficiently sensitive that you can begin to think about commercializing it and making it into an instrument that people can use. The atomic clock is much older. Atomic clock is 40, 50 years older and had a similar evolution over more than a decade to become a useful practical device. So there are many strands to your question, but it's money and people and understanding the science and then turning it into a real instrument.
Okay. We'll have one last question down in the front here. Gentleman with the green shirt. The microphone's just coming to you now.
Hi there. How do you capture a single atom and cause it to be used as a machine? How do you hold it?
Yeah, so I said so very little about that, though it's a subject close to my heart. So we use the laser light. So we begin. In the interferometer that uses whole atoms to navigate, I showed you a little red blob doing this. That was a cloud of about 10 million rubidium atoms in a vacuum system. So we pump all the gas out of a vacuum system. We then release some rubidium vapor by heating up some chemicals. And then we use laser light to collect and cool a cloud of these atoms. And at this point, although we have 10 million of them, they occupy several cubic millimeters. So the density of atoms is actually quite low. in the sense that they don't often bang into each other. They're not going to solidify and fall out as a lump of stuff. So it's an ensemble of almost completely isolated individual atoms. When we interrogate it and use it to make an instrument, we talk to all the atoms at once with our lasers. We read them out all at once. But each one is an individual interferometer. But we never, in that experiment, we never look at one atom at a time, which I think is what you were asking about. We could look at one atom at a time. And the way that we do that is to scatter light. So it turns out that these atoms will scatter light at a rate of 10 or 20 million photons per second. And that means you can get enough fluorescence from the atom to see one atom if you have a really good camera. And some of these clocks that I mentioned to you are actually made using single atoms, usually ions, where you just look at one. And again, it's suspended in a trap in a vacuum. Does that go some way to explaining? Yes. Yeah, good.
Okay, I think we probably have to bring it to a close at this point. I want to thank Ed, first of all, for sort of pulling back the curtain for us on the fascinating world of quantum physics. And as he mentioned, electrons and photons are very simple particles in many ways. They're all around us, and yet they're a lot of highly complex physics. And it's a real art to translate complex physics like that into the sort of lecture you heard today, where you can really make it accessible to a wider audience. And so we're deeply grateful for Ed being able to do that for us. I guess many of you will have added another word to your lexicon, interferometer. I bet you'll never forget it after this lecture. So please join me in thanking Ed again for what.